In this video, we're going to start talking about sigma and pi bonds. So remember valence bond theory, right? It says that when a covalent bond forms, we're going to actually overlap the orbitals. It could be our traditional sp-d orbitals, it could be our hybridized orbitals, but we're going to overlap orbitals. And then the electrons in the bond are found in that overlapping region. What sigma and pi bonds are essentially different ways that they can overlap. So a sigma bond first. So sigma bonds, and then we'll use our lower case Greek letter sigma. So sigma bond as our abbreviation. And these are considered the direct overlap. Sometimes it's called end-to-end. I usually use the term direct, but in the homework you may see end-to-end. Essentially, if you were to connect a line between the two nuclei, so draw a line connecting the two nuclei, we would call that our internuclear plane, right? Because it goes between the two nuclei. It's going to go through that overlapping region. So we can say the internuclear plane, right? The line connecting the two nuclei goes through the overlapping region. So an example for us, if I was to overlap two s orbitals, so I have an s orbital that's going to represent my nucleus in the middle. I'm overlapping with another s orbital, its nucleus in the middle. And then if I was to connect those two nuclei, right, draw a line right through them, that dotted line goes right through that area where they're overlapping, right through that overlapping region. I could take a p orbital and overlap it in this direction with another p orbital. Again, remember my nuclei are where there's this node, right, where there's no electron density. And then if I was to connect those two nuclei again, right, my internuclear plane, the line that goes between the two nuclei, that line is going right through this region here where they're overlapping. If I wanted to overlap an sp3, right, a little bit rounder, a little bit more mismatched than my p orbital. Again, my nuclei are going to be right here where this node is. If I was to connect those two nuclei, right, draw a line between them, that line again is going right through where they overlap. So those all would be considered sigma bonds. Sigma bonds are our direct overlap, right? Our internuclear plane goes through that overlapping region. My other type are pi bonds. So Greek letter pi as our abbreviation. And pi bonds are considered the sideways overlap. Sometimes called edge to edge. Again, I usually just use sideways, but edge to edge you will see, particularly in the more homework. Right up here, I didn't write it, but sometimes called end to end. I don't particularly like that again because an s orbital is spherical. You don't really think of a sphere as having an end, but that term has been used before. Again, I'm going to stick with direct overlap and then sideways overlap. The defining characteristic, though, is if I was to connect those two nuclei. So with pi bonds, my internuclear plane does not go through the overlapping region. So the internuclear plane, right, if I was to connect the two nuclei, does not go through the overlapping region. So an example for this one, and I can't do it with s orbitals, right? S orbitals, no matter how I rotate that sphere, if I connect those two nuclei, right, it's always going to go through that overlapping region. So s orbitals and another s orbital are only going to be able to form sigma bonds. And then honestly, an s orbital overlapping with something that's not s is also only going to be sigma, right? because an s orbital is a sphere, no matter how I rotate that sphere, it's always going to form sigma bonds. So if I was to take an S and this P, right, connect those two nuclei, it's going to go through, right, that connection is going through that overlapping region, right here where it overlaps. So s orbitals will never be involved in pi bonds, which means hydrogens will never have pi bonds, right? Only sigma bonds, because hydrogens only have an s orbital. So pi bond, an example of this one, I'm going to take p orbitals and I'm going to overlap them sideways. So I'm going to take this one and I'm going to overlap in this direction. So they're overlapping here, right? It wasn't a very good overlap, but they're overlapping there, and they're also overlapping here. My nuclei, however, are in the where that node is, right? And if I was to connect those, that line is not going through, right, these regions where they're overlapping. So my internuclear plane does not go through the overlapping region. So a single bond, right, a single covalent bond is always going to just be a sigma bond. So if you have a single bond, it's always going to be a sigma bond. So a single covalent bond is always going to be sigma. If you have a double covalent bond, it's actually going to have one sigma bond and one pi bond. And we will look at a structure here in a minute so you can see it. A triple bond is actually going to contain one sigma bond and then two pi bonds. And this is going to be true every time we see these. So a single bond will always just be sigma, right? It'll involve the direct overlap of our orbitals, right? If we were to connect a line between the two nuclei, it's going to go right through that overlapping region. A double bond is going to contain one bond just like that, right? One sigma, and then also one pi bond. A triple bond is going to contain one sigma bond and then two pi bonds, right? Because I'm sharing 6 electrons, I need to have 3 places where they're overlapping, right? And in one place it's going to be overlapping directly, and then in 2 separate instances they're going to be overlapping sideways, right? Where my internuclear plane does not go through that region where they're overlapping. So let's look at an example. So I want to look at 2 carbons. They're going to be bonded to each other, and then I'm going to put hydrogens on both of those carbons. And this is the correct geometry because each carbon, right, I have 2 central atoms, and we had said that we would do the geometry for them separately. So each carbon has 3 electron groups, right? My carbon on my left has this single bond, and then this double bond, so 3 electron groups. The carbon on the right also has 2 single bonds, right? A single bond to hydrogen, a single bond to another hydrogen, and then this double bond, so 3 electron groups. So both of those carbons are trigonal planar. So I drew this flat, right? This was that basic trigonal planar shape, and then this one is also trigonal planar. Nothing's coming out at us, nothing's going back, right? I didn't use any wedges or dashes. And then the hybridization, remember we had said that if it was sp2 hybridized, if it had 3 electron groups, it's going to be sp2 hybridized. So sp2, right, because it has 3 electron groups, and then also sp2 because it has 3 electron groups. And then if we remember, when we form sp2 orbitals, right, we're taking one s and 2 p's, right, that's where it's getting the name from. And we're going to have 3 of those. So each of those carbons have 3 sp2 orbitals. And then remember, we do have this one unhybridized p orbital. So each of those carbons also has a p orbital. Hydrogen can't be hybridized, right? If I was to look at hydrogen, right, this is carbon. I didn't put my shell number, but it would be 2, right? Because my valence electrons in carbon are in my second shell. If I was to look at hydrogen, Hydrogen only has an s orbital, so there's nothing to combine it with, right? Hybridized orbitals are combinations. I only have one orbital, so I can't combine it with anything. So again, remember, hydrogens will always be unhybridized. I can't hybridize an orbital when there's only one of them, right? I can't combine it with anything. So kind of bear with me here while I draw this picture. It's going to look kind of messy. And I won't ask you to draw this. If you get to organic, you need to. Now, I just want you to see what it looks like. And the book has a better picture than what I'm going to draw, so please also look in the textbook. But what I'm going to do is I'm going to look at each carbon, and I'm going to draw my C kind of small because I'm just going to use it to represent where my nucleus is. So where that C is my nucleus. And this is my left carbon. My left carbon has 3 sp2 orbitals. And remember, sp2 orbitals do have 2 lobes, right? They're kind of mismatched and they're pretty round, but they do have 2 lobes with a node in the middle, right? This is where my nucleus would be in the center here, where I'm putting this pink dot, right? That's where my nucleus would be. So where that pink dot is, that's my C. When I draw my 3 sp2 orbitals, I'm actually not going to draw this part. I'm only going to draw 1 lobe. So remember, it does have 2 lobes. It's just that the picture gets really messy, so it's standard to only draw half of it for the hybridized orbitals. I am going to put the p orbitals on here, and we are going to draw both lobes for that one. So carbon, it has 3 sp2 orbitals, right? That's these. And they're arranged in a trigonal planar fashion, so I want to do that. And they should all be similar in size. And again, you know, they would have their corresponding other lobe. I'm just leaving them off. Hydrogen is an s orbital, so I'm overlapping here to form a hydrogen, and then I'm also overlapping on the other side to form a hydrogen. I'm just going to redraw these one more time because I do want the sizes to be... They're all the same shell, same hybridization, so they should have similar sizes. And then overlapping with that hydrogen. So those would be sigma bonds I just drew, right? If I was to put my nucleus, this is where the nucleus is. If I was to connect those, that's a sigma bond, right? We said single bonds are always sigma bonds, and that's representing a single bond. I want to get that red out of there. This picture is going to be messy enough, so try to keep it simple. My other carbons, my carbon on the right, it also has 3 sp2 orbitals. I am going to come back and put my p orbitals on here. So one of those sp2s is overlapping with the other sp2 of carbon to form the sigma part of that double bond, right? Double bonds here we said have a sigma bond and a pi bond. That's my sigma part, right? If I was to connect those 2 nuclei, goes right through that overlapping region. So that's my sigma bond for that one. My other 2 sp2 orbitals, again, I want to arrange them so they're trigonal planar, and then I'm going to overlap them with my hydrogen orbitals, right? My s orbitals of hydrogen, forming 2 more sigma bonds. So I'm missing my p orbitals. So each carbon also has a p orbital. So I'm going to draw that p orbital on there. And the p orbital actually would be perpendicular to the plane of my sp2 orbitals. So if they're flat, right, if nothing's coming out, nothing's going back, then one half of this would be coming out, and then the other half would be going back. I'm not going to really worry about showing that much detail, but they would be perpendicular to that plane. So my p orbitals. And they should be, I'm just going to try to make it a little bit neater. The nucleus is in the same spot, and it looks like I'm overlapping that sp2, but again, I'm not, because it's 90 degrees, right? It's perpendicular to it. And then these 2 actually overlap sideways. So because they're spaced out on the 2 carbons, this is kind of how we show them forming that pi bond, right? They're overlapping sideways. If we could show them closer, right? They're overlapping, right? That's not a very good overlap, but they're overlapping like this. So they're overlapping here and here. My nuclei is in the middle, so it doesn't go through it. And then be careful, they're overlapping in 2 spots, but it's 1 pi bond, right? These guys are overlapping here, and they're overlapping here, but this is one pi bond. So if I was to label my structure, I just want to get some of this out of the way. We'll keep this here. So this would be a pi bond. Don't do this because now I've labeled 2 pi bonds and it really has 1. So either the top pi or the bottom pi, but it's the same bond. So I have 1 pi bond, 1 sigma bond, that's my double. And then this is a sigma, this is a sigma, sigma, and sigma. If we were to count the number of sigma and pi bonds on this molecule, I would say I have 1, 2, 3, 4, 5 sigma bonds. And then I have 1 pi bond. So again, I won't ask you to draw this. This is our orbital bonding picture, but I do expect you to be able to look at this and be able to tell me the number of sigma and pi bonds that it has. And again, we're really just using this to remember. So every single bond is going to be a sigma bond. A double bond is going to have 1 sigma and 1 pi bond. A triple bond is going to have 1 sigma bond and 2 pi bonds. So looking back at this one we just did, I would say I have 1, 2, 3, 4, 5 sigma bonds. Notice I counted that double bond once because the double bond has 1 sigma, so 5 sigma. And then the double bond also has 1 pi, so 1 pi bond, right? A double bond counts as 1 sigma and 1 pi bond. Let's do another one. I'm gonna draw something kind of big and messy, and we'll go through and we'll determine the number of sigma and pi bonds that it has. And actually for practice, let's figure out the hybridization also of each atom that can hybridize. So just bear with me as we draw something kind of big. So carbon, let's bond it to 2 hydrogen and another carbon. And a triple bond to a carbon. Make those carbons octet. Carbon, oxygen, hydrogen, and then I have 2 lone pairs on that oxygen. So we're gonna do hybridization first. And remember, hydrogens can't hybridize their orbitals, right? They only have an s orbital, so I can't combine it with anything else. So essentially you can ignore the hydrogens. For the rest of them, I'm just going to count the number of electron groups. So nitrogen here, right? It has 1, 2, 3, 4 electron groups. Remember, a single bond, a double bond, a triple bond, and a lone pair are 1 group each. So this has 3 single bonds and a lone pair, so 4 electron groups. If it has 4 electron groups, it's sp3 hybridized. So nitrogen would have 4 sp3 orbitals, right? 2 of them would be overlapping with the s orbital of hydrogen. 1 of them would have a lone pair in it, and then the other would be overlapping with whatever the hybridized orbital of that carbon is. This carbon, it happens to be sp hybridized, right? I have 1 electron group. Remember, a triple bond counts as 1 group. It's in 1 position, if you think about it that way, right? It's constrained between those 2 atoms. So I have 1 spot where those electrons are, and then this single bond, so 2 groups. I would like you to do the rest of it yourself. So please hit pause, go through and label the hybridization on all of the other atoms that can hybridize, right? Hydrogen can't. And then when you're ready, hit play again and you can check your answers. Okay, so hopefully you guys did that. So this has 2 electron groups, so sp. This carbon has 4 electron groups. 4 electron groups are going to be sp3 hybridized. This carbon has 3 groups, 1, 2, 3. That double bond counts as 1 group. So 3 groups are going to be sp2. This carbon also has 3 groups, so sp2. This carbon also has 3 groups, so sp2. And then this oxygen also has 3 groups, right? Double bond is 1, and then the 2 lone pairs are 2 more, giving me 3 total. So that is going to be sp2 also. I am going to erase all the work that we just did. I just want it to be a clearer picture when we go and mark it up for our number of pi and sigma bonds. So our question is, how many sigma bonds do we have? And then how many pi bonds do we have? So we want to remember that single bonds are sigma bonds. A double bond is 1 sigma, 1 pi, and then a triple is going to be 1 sigma and 2 pi. So I'm going to go and kind of cross stuff as we count them. So for sigma bonds, I'm essentially going to count every bond, right? My double bond has a sigma as part of it. My triple bond also has a sigma as part of it. So we're literally just going to count everything. So I have a bond here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that gives me 14 sigma bonds. And then pi bonds, I'm going to count once for my double bond, right? Because a double bond contains 1 pi bond. And then I'm going to count twice for the triple bond because the triple bond contains 2 pi bonds. So for my triple bond, 1, 2, and then 3, 4. So I have 4 pi bonds in this structure. So 14 sigma and 4 pi bonds.